as given by equation 3 will also be constant. Hence, the electric field strength E at any distance r from the source charge Q is independent of the test charge Q0. It varies with r cap and is inversely proportional to r square. The electric field at any point in the electric field is finite and is zero only when distance r is equal to infinity. In the electric field of a positively charged particle, the electric field strength vector E at any point in the field always points away from the charged particle in a radially outward direction. The point charge Q0 will be accelerated in the direction of the electric field as it experiences an acceleration A due to the force due to the electric field, and the acceleration is expressed as A is equal to Q0 E by m, where m is the mass of the particle. In the field of a negatively charged particle, the electric field strength vector at any point in the field always points towards the charged particle in a radially inward direction. Here, the point charge Q0 in this electric field will be accelerated in the direction opposite to the electric field. The magnitude of acceleration of Q0 is the same regardless of whether the electric field is due to source charge plus Q or minus Q. For a charge Q, at all points on an imaginary sphere of radius r around it, the electric field strength will be equal in magnitude and will be equal to 1 by 4 pi epsilon naught Q by r square. There is a spherical symmetry with respect to the magnitude of the electric field strength E in the electric field of charge Q. Consider a region consisting of point charges Q1, Q2, Q3, Q4, and so on in air, or a vacuum with position vectors R1, R2, R3, and so on relative to the origin O. Let P be a point in this region. The net electric field strength E at point P is the superposition of all the electric field strengths E1, E2, E3, E4, and so on due to the individual charges. The net electric field strength E at point P will be equal to the vector sum of all the electric field strengths E1, E2, E3, E4, and so on. Then, E is equal to 1 by 4 pi epsilon naught into Q1 by R1 P square into R1 P cap plus Q2 by R2 P square into R2 P cap plus Q3 by R3 P square into R3 P cap and so on. Here, R1P is the distance from Q1 to P, and R1P cap is the unit vector in the direction of Q1 to P. R2P is the distance from Q2 to P, and R2P cap is the unit vector in the direction of Q2 to P, and so on. The net electric field strength E can now be written as 1 by 4 pi epsilon naught sigma I1 to N Qi by RIP square into RIP cap, where RIP cap is the unit vector in the direction of the net electric field strength E. Consider a situation where charge Q is accelerating. Then, it produces electromagnetic waves, which propagate at the speed of light. Here, Q0 is also accelerating in the electric field of Q, and there will be a force on Q0 due to the electric field of Q. This force on Q0 due to Q is actually caused by the electromagnetic waves generated by the accelerating charge Q, and which travel from Q to Q0 at the speed of light. Thus, an accelerating charged particle is a source of electromagnetic waves. For example, electric current applied to a solenoid creates an electromagnetic field around it. Consider a region consisting point charges Q1, Q2, Q3 and so on in air or in vacuum, with position vectors R1, R2, R3 and so on relative to the origin O. Let P be a point in this region. The net electric field strength E at the point P is the superposition of all the electric field strengths E1, E2, E3 and so on due to the individual charges Q1, Q2, Q3 and so on respectively. Now, R1P is the distance from Q1 to P, and R1P cap is the unit vector in the direction of Q1 to P. R2P is the distance from Q2 to P, and R2P cap is the unit vector in the direction of Q2 to P. R3P is the distance from Q3 to P, and R3P cap is the unit vector in the direction of Q3 to P. The net electric field strength E at the point P will be equal to the vectorial sum of all the electric field strengths E1, E2, E3 and so on. Therefore, E is equal to 1 by 4 pi epsilon naught into Q1 by R1P square into R1P cap plus Q2 by R2P square into R2P cap plus Q3 by R3P square into R3P cap and so on. The net electric field strength E can now be written as 1 by 4 pi epsilon naught into sigma I equal to 1 to N Qi by RIP square into RIP cap. In many practical situations, electric fields are produced by continuous charge distribution on the surfaces of the bodies of finite size and not due to the charge distribution discussed earlier. A few examples of some practical situations are a line charge distribution, a sheet of charge, or a volume charge distribution. Since it is difficult and impractical to work with discrete charges in terms of the microscopic locations of the charge distributions, to evaluate the electric field at a point, we adopt a different approach. In such situations, the entire charge distribution is assumed to be made of infinitesimally small elements, and the electric field strength at any point in the electric field will be equal to the vectorial sum of the electric field strengths due to each such small element. Let us look at a line charge distribution of length L carrying a charge Q as shown. If we consider a small element of such a charge distribution having a charge delta Q and of length delta L, the linear charge density, lambda, of such an element is equal to delta Q by delta L, since it is the charge per unit length. The SI unit of linear charge density, lambda, is Coulomb per meter. It is a scalar quantity. If a line charge distribution is carrying a non-uniformly distributed charge, then its linear charge density, lambda, for an individual element is equal to delta Q by delta L. if a conductor of length L is carrying a uniformly distributed charge Q, then its linear charge density lambda is equal to Q by L. Now let us consider a sheet of charge carrying a total charge Q on a surface area A. In such situations, the electric field strength at an imaginary point P can be calculated by assuming the charge distribution to be divided into infinitesimally small areas, each having an area delta A and charge distribution delta Q. Surface charge density sigma is the charge per unit surface area. Therefore, surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. It is a scalar quantity measured in coulomb per meter square in SI unit. If charges are non-uniformly distributed, surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. If the charges are uniformly distributed over the surface, then the surface charge density, sigma, is equal to Q by A. Now let us consider a volume charge distribution. Consider a volume V carrying a charge Q. Let us assume that the total volume is divided into a number of small elements, each of volume delta V having a charge delta Q. Then, volume charge density or charge density rho of such a volume charge distribution is defined as the charge per unit volume. Thus, rho is equal to delta Q by delta V and is measured in coulomb per meter cube in SI unit. It is a scalar quantity. If charges are not uniformly distributed, the charge density rho for an individual volume element is equal to delta Q by delta V. If the charges are uniformly distributed, the volume charge density of the conductor is expressed as rho is equal to Q by V. Now consider the small volume element delta V of charge distribution carrying a charge delta Q. We know that the charge density rho is equal to delta Q by delta V. Thus, charge on the volume element is then delta Q equal to rho delta V. The position vector of the volume element delta V with respect to the origin O is R. Consider a point P in the electric field of the volume charge distribution, which is at a distance of R' from the volume element delta V. The electric field strength at point P due to the volume element is delta E is equal to 1 by 4 pi epsilon naught delta Q by R' square into R' cap, where R' cap is the unit vector in the direction of the straight line from the volume element towards the point P. This can be written as delta E equal to 1 by 4 pi epsilon naught into rho delta V by R' square into R' cap. Now, the electric field strength E at P due to the total volume charge distribution is equal to the vectorial sum of the electric field strengths due to all individual volume elements. However, this is impractical as there would be many infinitesimal volume elements at varying distances from the point P. Hence, to obtain the electric field strength E due to the total volume charge distribution, we integrate delta E within suitable limits, A to B, under the assumption that the volume elements have very small volume tending to zero. Consider a point charge plus Q and its electric field. Let us introduce a unit positive charge at a point P1 in the electric field of Q. As both the source charge and the test charge are positive, this unit positive charge placed at point P1 follows the path P1A in the electric field due to the repulsive force on it exerted by the electric field of the source charge. Thus, path P1A represents an electric line of force or an electric field line. An electric field line represents the path followed by a unit positive charge in an electric field. Repeating this procedure for various points in the electric field, we obtain the electric field lines around the charge. Electric field lines are used to represent the electric field of a charge or a system of charges pictorially. In fact, the electric field lines follow the same direction as the electric field vector at any point in the electric field. As any electric field line is the path followed by a unit positive charge in an electric field. If we draw all the electric field lines for the electric field of the given source charge Q, the electric field lines appear as shown. One of the most important characteristics of electric field lines is that they help us estimate the electric field strength. The relative density or closeness of the field lines at different points gives an indication of the relative strength of the electric field at those points. The field strength is stronger at places having more crowded field lines than at places where they are less crowded. To illustrate this, let us now consider two regions, A and B, of same area placed normal to the field lines in the electric field. The field lines in region A are relatively closer than those in region B. The number of field lines passing normal to an area is proportional to the magnitude of the electric field strength at these points. This indicates that the strength of the electric field at A is greater than the field at B. As the electric field strength is stronger in region A and weaker in region B, the electric field shown is a non-uniform electric field as the field strength varies from region to region. To understand the dependence of field lines on area, let us understand the relation between the area of the element and the solid angle created. For this, first let us understand the term solid angle. Solid angle is a measure of a cone. When the intersection of a cone with a sphere of radius r is considered, the solid angle delta omega subtended by the area element is defined as delta S by r square, where delta S is the area on the sphere, which is the area element cut out by the cone. Let this be equation 1. Therefore, delta S is equal to r square into delta omega. Let this be equation 2. For a given solid angle omega, the number of radial field lines is the same. At two different points, say x and y, in the electric field, which are at distances r1 and r2 from the charge, we observe that the area of the elements subtending the same solid angle delta omega will be delta S1 equal to delta omega into r1 square at x and delta S2 equal to delta omega into r2 square at y respectively. The number of field lines, say n, passing normal to delta S1 and delta S2 is also the same. The number of field lines passing normal to a unit area is equal to the electric field strength E. Therefore, the electric field strength E1 at x will be equal to number of field lines per unit area at x, which is equal to n by delta S1 or n by R1 square into delta omega, using the value of delta S1. Let this be equation 3. Similarly, electric field strength E2 at y is equal to n by delta S2 equal to n by R2 square into delta omega. Let this be equation 4. If we divide equations 3 and 4, we see that the ratio of the electric field strengths at x and y is equal to R2 square by R1 square. Hence, we can conclude that the electric field strength due to a point charge varies inversely to the square of the distance from the charge. From equations 3 and 4, we see that even though the number of field lines n and the solid angle delta omega are the same at x and y, the electric field strength E, which will be equal to number of field lines per unit area, is proportional to 1 by r square, where r is the distance of the point from the charge q. Earlier, you have learnt that the electric field strength vector of a positive charge, say plus q, always points in a radially outward direction, and the electric field strength vector for a negative charge, say minus q, points in a radially inward direction. Thus, we see that the electric field lines for a positive charge diverge normally from the charge, and those for a negative charge converge normally towards the charge. Let us now visualize the electric field lines for a system of two positive charges, say plus q each. From the field lines, we can see a very clear picture of the repulsion existing between the system of charges shown. The electric field lines also help us in visualizing the electric field of a dipole consisting of charges plus q and minus q. We observe that the electric field lines for an electric dipole are continuous lines extending from the positive charge to the negative charge. From the field lines, we see very clearly the force of attraction existing between the system of charges in the dipole. Thus, we see that the field lines convey a very clear picture of the nature of the electrostatic forces existing in any system of charges. From these examples of various charge configurations, we observe the following properties of electric field lines. The tangent drawn to an electric field line at a point in the electric field gives the direction of the electric field strength E at that point. The direction of the tangent at a point indicates the direction of the force on a unit positive charge at that point, and hence it gives the direction of the electric field strength at that point. For the electric field created by a system of positive and negative charges, the field lines begin at the positive charge and end at the negative charge